All right, let's just dive right into this explainer with a truly terrifying hypothetical inspired by a recent Science News article. I want you to picture the night sky for a second. For pretty much all of human history, the stars and planets have been this ultimate symbol of clockwork predictability. But actually, the universe is way more chaotic than our quiet little corner of the galaxy makes it seem. Today, we're going to explore a topic that honestly sounds like pure sci-fi, but it's absolutely a cutting-edge field of astrophysics. We're talking about the violent, chaotic dynamics of rogue planets, gravitational captures, and literally stolen moons. Just imagine the visceral horror of a passing star violently kicking our planet right out of the solar system. No warning whatsoever, just some rogue star wandering a little too close to our sun and its massive gravity completely disrupting the delicate balance of our neighborhood. In an instant, Earth is ejected from the only home it's ever known, sent hurtling out into the freezing, pitch-black void of deep space as a rogue planet. It's a completely chilling thought, right? But to really grasp how something like this happens, we have to look closely at the mechanics of these cosmic interactions. Section 1. Did we steal Planet 9? So before we get to the terrifying reality of planets being kicked out into the void, let's actually flip the script for a second. Because if planets can be thrown out, well, they can also be caught. And there's this really compelling theory that our own sun might actually be guilty of a little cosmic kidnapping itself. We call this gravitational capture. It's basically the mechanism that allows a star to snatch up a free-floating rogue planet as it just wanders by. Out there in the Milky Way, there are potentially billions of these orphaned, starless planets drifting through the dark. And if one of them happens to pass by a star at just the right angle and speed, it doesn't just fly past. The star's gravitational net catches it, forcing it into a stable orbit. So it goes from being a completely free-roaming nomad to a bound satellite. Now, you might be thinking, okay, the chances of a star catching a speeding planet have to be vanishingly small, right? Well, researchers at New Mexico State University ran some incredible computer simulations to test this exact scenario. And they found a surprising 40% probability that a rogue planet entering our solar system would be successfully captured by our sun. I mean, think about that. 4 out of 10 times, that wanderer becomes a permanent resident of our system. This soft capture scenario, where a new planet basically moves in without kicking any of the existing planets out, is exactly what Caltech planetary scientist Konstantin Batygin believes could explain the mysterious origins of the elusive Planet 9. He points out that the number of seemingly unrelated puzzles within the solar system that get resolved by Planet 9's existence is just too great to be a coincidence. For years, astronomers have observed these strange gravitational anomalies out at the edge of our solar system, pointing to a massive, hidden ninth planet. And Batygin argues it's entirely plausible that this isn't a native planet at all, but instead it's a stolen exoplanet that our sun snagged billions of years ago. However, the universe isn't always so gentle. What about the other 60% of those simulations? Well, lead researcher James Vester coined the perfect phrase for this: rogue in, rogue out. In these cases, a slingshot effect happens, where the invader is just violently ejected back out into deep space. But here's the truly terrifying part of that. In at least 10% of those slingshot scenarios, the departing wanderer's gravity is so intense that it literally drags an existing, native planet into the dark with it. Section 2. The Cosmic Billiards Table. And that brings us to this fascinating new astrophysical paper from Archive that treats these stellar encounters like, essentially, a chaotic game of cosmic billiards. Because when a star buzzes a planetary system, it doesn't just mess with the planets. If those planets have moons, the physics get incredibly complicated and, frankly, incredibly dangerous. As you'll see here, the geometry beautifully illustrates the initial setup for the researchers' N-body simulations. We've got an incoming field star moving at a pretty typical stellar cluster speed of 3 kilometers per second straight towards a host star. Orbiting that host star is a Jupiter-mass giant planet, which in turn has its very own Ganymede-mass moon. The researchers basically ran tens of thousands of these scattering experiments, constantly tweaking the approach angles and distances just to see exactly who survives the encounter and who gets thrown out into the void. By comparing these trajectories, we see 2 vastly different outcomes from the simulations. On the left, we have what is called a free-floating planet-moon pair. Basically, the gravity of the passing star kicks the planet out of the system, but the moon somehow manages to hold on, and they escape into deep space together as a pair. But over on the right, it's a totally different story. The intense gravitational shear of the encounter just rips the moon away entirely. The planet gets ejected and the moon gets ejected separately, both of them doomed to wander the galaxy totally alone.
Section 3. Can moons survive the journey?
So the absolutely crucial point here is what exact orbital conditions allow a moon to survive this violent ejection without being stripped from its host planet? Why do some moons hold on for dear life while others just get torn away in the cosmic crossfire? Well, distilling the dense data from the study, we find a very clear pattern. Survival is all about distance. More specifically, it depends on the moon's semi-major axis relative to the planet's hill radius. The hill radius is basically that bubble of gravitational dominance the planet holds. Tight, close-in moons, kind of like Jupiter's moon Io, have a near 100% survival rate. They are hugged so tightly by their planet that the passing star just can't pull them away. But moons orbiting further out, beyond 45% of that hill radius, are almost always ripped away. And even worse, if you do somehow survive as a wide-orbit moon, your orbit is left highly erratic, stretched out and chaotic, a process known in physics as intense dynamical heating. Now, what's really interesting is how this data compares to completely different ways a planet can be ejected. The stellar encounters we've been talking about actually preserve moons incredibly well across all separations. But compare that to planet-planet scattering, which is when planets within the exact same system gravitationally kick each other out. This chart essentially proves that planet-planet scattering is highly destructive. Long story short, if you're a moon, you'd much rather your planet get kicked out by a random passing star than by one of its own sibling planets. Section 4, Finding Moons in the Dark. Okay, let's see how all of this builds into real-world observations. Because it's one thing to run computer simulations all day, but it's another thing entirely to actually find these exiled worlds. Amazingly, these free-floating planet-moon pairs aren't just mathematical theories. We might have already detected one floating out there in the Milky Way. Back in 2014, astronomers spotted a microlensing event known as MOA 2011 BLG 262LB. Microlensing happens when a massive object passes in front of a background star and its gravity actually magnifies the star's light. But the light curve from this specific event was really bizarre. It basically has two degenerate interpretations in the data. It could either be a high-velocity binary planet system, so two planets locked in a dance with absolutely no star, or, and this is where it gets super exciting, it could be a rogue Jupiter harboring a hidden sub-Earth mass exomoon. If it really is a rogue planet with a moon, we can actually use the physics from this new study to act like cosmic detectives. Scientists used cross-section mapping to statistically deduce the entire history of this object. Because the moon survived, and based on the specific distance between the planet and the moon, they calculated that this Jupiter-sized world was originally violently ejected from an orbit about 5.2 astronomical units away from its parent star, which is, crazy enough, remarkably close to our own Jupiter sits today. They essentially reverse-engineered a cosmic eviction that happened millions or maybe even billions of years ago. I want to leave you with this final, genuinely provocative thought. We normally assume life absolutely requires a sun, right? But if a rogue moon survives that traumatic journey into deep space, locked in a tight orbit around a giant gas planet, it actually wouldn't freeze completely. The immense tidal gravity of the host planet would constantly squeeze and stretch the moon, creating incredible internal friction. This tidal heating could easily melt its subsurface oceans, creating hydrothermal vents. Meaning, right now, as you watch this explainer, there might be hidden, isolated worlds wandering the galaxy, absolutely teeming with alien life in the total, freezing darkness of deep space. Pretty wild, right?